Climate change and adaptation, observe changes in its causes, unit 2. Let's come to the fourth and final module of this unit, climate modeling. How do the modeling of the climate takes place? Let's start with 100 parts of the solar energy. Which is mostly in a short wave range. 21% of that is reflected back out to the space from the cloud top. Then 7% back scattered by the atmosphere back to space again. Another 3% reflected by the Earth's surface. So 21 plus 7 plus 3, 31% of this short wave solar energy received and reflected back to the space, out of the space. This is what is considered to be the Earth's albedo, 0.31. Out of the rest, again 3% absorbed by the stratospheric ozone. Another 18% is absorbed by the rest of the atmosphere, that is by dust and gases, and 3% is absorbed by the cloud. Thus a total of 3 plus 18 plus 3, 24% absorbed somewhere in atmosphere. What happens to the rest? 69 minus 24, 45% solar radiations. 25% is directly absorbed by the Earth's surface. Another 20% diffused radiation scattered from the atmosphere is again received by the Earth. It is because of this preferential scattering by the atmosphere in the wavelengths corresponding to blue light, the Earth sky looks blue. This is short wave budget of the atmospheric radiations. Short wave is the radiation which receives from sun, how the distribution takes place. Here I have seen 25% direct plus 20% diffused, thus totaling 45% solar radiation absorbed by the Earth, 3% by cloud and 18% by atmospheric dust and gases, thus totaling 21% radiation absorbed by the atmosphere, as well as 3% radiation absorbed by the stratospheric ozones, thus accounting 69% radiations, with the very amount which remained after the 31% radiation reflected by Earth atmosphere. Now this 69% radiation, when released, takes the form of long wave radiations because of much lower temperature compared to sun. So because of temperature, the wavelength depends. With high temperature in the sun, the wavelength is much lower, and Earth is much lower temperature, so wavelength is higher. By Planck's law. Let's see how the long wave radiations balance takes place. We have seen already the 45% directly diffused radiations absorbed by the Earth's surface, which has to be released. Similarly, 21% radiation absorbed by the Earth's the atmospheric dust, gas and clouds. This also need to be released. And 3% radiations absorbed by the stratospheric ozones, which has to be released. All of them in long wave radiations. Out of the 45% radiation released from the Earth, a long wave, 90% is utilized a latent heat transfer, that is water evaporating from the surface, which rises into atmosphere and finally resulting in precipitations. 4% of the Earth's radiation is delivered onto the atmosphere in the form of convective motions, that is the large scale wind patterns, storm, atmosphere disturbances and so forth, that transports heat into the atmosphere. Interestingly, 110% of the long-wave infrared radiation leave the surface. 110 means more than 100%, so making somewhat chilled. Yet 96% returned back through the greenhouse effect to the surface, and thus remaining 100 minus 96 and 14% is the net loss of the heat from the earth that is emitted into space. Another 8% make it all the way out of the space in the form of long-wave radiation emitted from the Earth's surface. So totally 19 plus 4 plus 14 plus 8, the summing out of 45% the Earth radiation, which is exactly same as the radiation received. Besides this 45% long-wave radiation released from the Earth, another 21% long-wave radiation is released from the atmosphere, dust, clouds, back again to the atmosphere. Plus another 3% radiations are released back to the atmosphere. Thus the total long-wave radiations. Thus the total long-wave radiation released on the atmosphere 19 plus 4 plus 14 plus 8 plus 21 plus 3, so 69%, which is the same quantity that has been observed by the Earth. Now, based on the conception, we start the climate change modeling. Essentially, climate models are the extension of weather forecasting, whereas the weather models make predictions over specific areas and short time spans. Climate models are broad or analyze long time spans. They predict low average conditions that will change in regions over the coming decades. Climate models include more atmospheric, oceanic and land processes than weather models, because this weather model deals mostly with the ocean circulation and melting glaciers. These models are typically generated from mathematical equation that uses thousands of data points to simulate the transfer of energy and water that takes place in the climatic systems. Scientists use the climate models to understand the complex Earth systems. These models allow them to test hypotheses and draw conclusions in the past and future climatic system. This can help them to determine whether the abnormal events or storms as a result of the change in climate or just as routine climatic variations. For example, when predicting the tropical cyclone during the hurricane seasons, the scientists can use the climate models to predict the number of tropical storms that may form off the coast and what region they are likely to make the landfall. When creating the climate model, scientists use one of the three common methods, like energy balance model, then immediate complexities model, and general circulation model. These models use numbers to simplify the complexities that exist when taking account of all the factors that affect the climate, like atmosphere mixing and ocean currents. Energy balance model helps to forecast the climate change as a result of Earth's energy budget. This previous slides we saw the energy budget of the Earth. This model takes into account the surface temperature from the solar energy, albedo and reflectivity, and natural cooling from Earth, emitting heat back out into space. To predict the climate, scientists use an equation that represents the amount of energy coming versus going out to understand the changes in heat storage. For example, as more heat absorbing carbon dioxide fills the atmosphere, scientists take these equations to plug into a box model that represents this square land within a three-dimensional grid to express the climate in the regions or even across the continent. In this, we are going to discuss some basic about energy balance model. And most all the models, we simplified concept to look. This provides the frameworks for the climate systems as implemented in many climatic models. Modeling components include the forcing agents that pushes the activity to take place, feedback processes, carbon uptake process, radiative forcing and balances. The lines indicate the physical interconnections and solid lines, and feedback pathways are dashed lines. The principal changes, blue boxes, lead to climate impacts, and red boxes and feedbacks. The radiative forcing is the difference between the solar irradiation, the sunlight absorbed by the earth, and energy radiated back to space. Changes to earth's radiative equilibrium that causes the temperature to rise or fall over the decadal periods. They are called the climatic forcings. Simple climatic model. Usually model refers to simulation of real life state by physical or computational representatives, which can simulated and calibrated iteratively into real life situations so as to employ for the projection onto the various scenarios. We'll start our discussion of the climate models with simplest possible conceptual model for modeling the Earth's climate. These models include different variants of so-called energy balance model and energy balance EBM. Energy balance model or EBM doesn't attempt to resolve the dynamics of the climate systems at the large scale, wind or atmospheric circulation systems, ocean currents, convective motions in the atmosphere and the oceans, or any number of other basic features of the climate system. Instead, it simply focuses on the energetics and thermodynamics of the climate systems. So we'll start with the zero-dimensional EBM, the simplest model that can be involved to explain, for example, the average surface temperature of the Earth. In the very simple model, Earth is treated as a mathematical point in the space, so as to say. There is no explicit accounting for the latitude, longitude, altitude. Hence, we refer such model as zero-dimensional. Zero-dimensional EBM, we solve only the balance between incoming and outgoing sources of energy, radiations at the surface. We'll then build up little bit more complexities, taking into account of the effect of Earth's atmosphere, in particular the impact of the atmospheric greenhouse effects, through the use of so-called gray body variants of the EBM. We'll assume that the outgoing long-wave radiation is given simply by treating the Earth as a black body. Black body means the body that absorbs all radiation incident upon it. We'll also assume that Earth's temperature is maintained, that is the radiation incoming radiation equal to outgoing radiations. So what is the incoming radiations? Incoming radiation, in the first model we'll explore that EIN is equal to pi r square S, where r is the Earth's radius, S is the energy flux density, and is equal to 1367.6 watt per square meter. So when you multiply the area, so it get this many watts of the energy reaching on the Earth's surface. And because this is what you observe, this value is observed from the satellites. Because from sun's point of view, Earth looks like a disk of surface area pi r square. So pi r square into S. What is the incoming radiation? Outgoing radiations, no? Four pi r square sigma t to the power fourth. Because the Earth's total surface area 4 pi r square, the surface area of the sphere, which is used to release. It's not only that one previously pi r square, because that is the circular part which exposed to sunlight, but 4 pi r square because then this heat is released from the Earth's overall surface. So 4 pi r square. And it follows the black, we assume it's for the black body. So as per black body radiations by Stephen Boltzmann's law, here the outgoing radiation is proportional to fourth power of the temperature in Kelvin, and proportionally constant sigma is Stephen Boltzmann's constant, which is equal to 5.67 into 10 to the power minus 8 watt per square meter per Kelvin to the power fourth. So now both equate, because this is the total heat energy received, this energy releases, radiation received and releases. So by equating incoming outgoing radiations and solving, we'll find s to the power fourth. S by fourth is equal to sigma t to the power fourth. It is customary to refer s by 4 as q. Remember, we talk s as the energy flux density, so it's a constant. So by 4 is also another constant, so assume that q is a 1/4 of the energy flux density, q. So in that case, equation become q equal to sigma t to the power fourth, or temperature is equal to q by sigma to the power 1/4. Now you can substitute the value of q and sigma, then you will find the Earth's surface temperature will come out to be 278.7. So this is about 5.5 degrees centigrade. The value of 5.5 degrees centigrade seems to be reasonable, but is not in agreement with the known average temperature of the Earth, which is about 16 degrees centigrade. So definitely need a better model. So how to go about it? Well, in model 1, we omitted number of important parameters. First factor we want to add now involves the reflections. Some of the incoming energy from the sun is reflected back into the space, snow, ice and cloud. Through that, some energy reflected back. For example, reflect a great deal of the incoming radiation with light, and we already know that that is the Earth albedo, around 0.3. So now you consider the incoming energy W, which will become pi r square minus 1 by alpha. Alpha is the albedo, which is reflected back, making the net radiation available for absorption to be 1 minus alpha. So the outgoing energy W will continue to be 4 pi r square sigma t to the power fourth. Now you equate them. And you solve for the t. And you get t equal to q into 1 minus alpha divided by sigma whole to the power 1 by 4. So if you are substituting the values here, albedo alpha is taken 0.3, and then we will find this will come out to be 254.9. That is the temperature. Although second model is better because in the sense it includes some physics, but the prediction of the temperature value in equilibrium is worse than the previous model. It predicting that the temperature will be minus 18.1 degrees centigrade, because 273 subtract from Kelvin to get the temperature, so we become minus 18.1 degrees centigrade. So I think I'm missing out something crucial. Let's see. Here we'll focus on outgoing radiation now. Guess what I missed? Right, missed greenhouse gases. We all know by now the greenhouse gases like carbon dioxide, methane, water, as well as dust and aerosols have significant effect on the properties of the atmosphere. However, the effect on the outgoing radiation is difficult to model. So how do you model the outgoing radiations? So what we can do, we can just reduce the Stefan-Boltzmann's law by some factors, assuming the greenhouse factor. That is one approach you can do, simplest approach you can do. Now epsilon is the greenhouse factor, so between it is by reducing the outgoing radiations, just returning something. So 0% to 100%, so between 0 to 1, so it will be some decimal points in between 0 to 1. So this is the factors which reduces the outgoing radiations. So incoming radiation remain as it was before, pi r square s into 1 minus alpha, and outgoing radiation becomes 4 pi r square epsilon is the greenhouse factor, epsilon, and sigma t to the 4th. So that is it. So epsilon, that decimal 0 to 1, it will reduce the outgoing radiations so that it can match. And equating them and solving for the temperature, we get the question similar to the previous model, except that epsilon is multiplied with the denominator. Okay. Same. Say the epsilon is multiplied with the denominator. But since we don't know what is the value of epsilon, we cannot estimate the temperature. So what we can do now? We don't know epsilon. So we'll try to use it to find out epsilon. I'll do that. We'll take alpha as 0.3 with the value, and global temperature we will take 288 Kelvin, means around 16 degrees centigrade. So you put the global temperature and recalculate what epsilon you are going to get. So for that we'll find epsilon comes out to be 0.66. This is how you readjust to the existing temperature and to find out what are the greenhouse contributions. So 0.66 is the greenhouse factor. If epsilon values become increased, okay, then what will happen? More and more will be going outside. It's outgoing radiations, but reduce means less and less go outside, then more and more trapped. What happens if the combined effects of greenhouse gas, dust and aerosol reduces the parameter from 0.66 to 0.5, as you mentioned? Then what will happen? The equilibrium temperature T would increase. Why? The mean outgoing radiations decreased because it's not allowing to go outside. Epsilon is reduced means it is not allowing to go outside. So more it is trapped. What will expect Earth's temperature if energy inlet if the energy outlet? In the case, same thing happens because more energy coming, less energy going. So again heating. So all of them leads to what we call global warming. Now that you have got epsilon values and you have a model where you already fitted with the existing temperatures. But only thing is that so far you have constructed a system in equilibrium, that is input radiation, output radiation equal. But this is not necessarily so. To explore the relationship between the difference between input and output energies and planetary temperature, you have to make the model more dynamic. Let's consider that the temperature changes directly in proportion to energy imbalances. After making the equate, but it may not always equate, so because it may fluctuate. So what find out the difference between these two is a functionality of the temperature. Temperature changing with time will make the difference between the input energy and output energy. The difference between the two affects, it is a function of the temperature with time. And let's assume it proportional. That means rate of change of temperature with time is proportional to the difference between input and output energies which comes. If it is more, and the temperature is more, then the differential increased. Temperature less, differential decrease. That's quite reasonable. Now you will use the constant C as the planetary heat capacity, because proportional, you have to multiply constant somewhere, which connects the rate of change of the temperature to energy densities, which means ratio of the energy per square unit area, because that's what a Q refers to. S vapor is Q. So arrive at a ordinary differential equation ODE for the temperature T as a function of time T, small t. Now let's draw a graph. Our function of T, capital T, is equal to 1 minus alpha into Q minus epsilon sigma T to the power 4th. So that is the tool equation I got, and all the parameters you already know by now except temperature. So now change the temperature from 200 degree Kelvin to 400 Kelvin, and the epsilon value will keep as 0.66 and alpha is put to 0.3. So the equation will become Ft equal to 239.33 minus T to the 4th 3.7422 into 10 to the minus 8. This equation, you are substituting all the values. Now once you make the graph of that, this is how the graph comes. X-axis shows the temperature in Kelvin, as it is increasing. Ft the functions, the difference between the input and output, that's what made the function. So that keeps on going down. What is the vertical axis represent the physical world? Vertical axis refers to the rate at which the temperature changes, dt by dt, d capital T by d small t. Capital T temperature, small t time, rate of change of temperature with time. What is 0 of the Ft? The range between 200 to 400 degree Kelvin. Where have we seen this value before? What does it represent? Well, if you look there, Ft equal to 0 at T 288 Kelvin. This 288 Kelvin is what? The actual temperature of the earth, which we have used in previous model. Now, if temperature 300 degree Kelvin, do you expect the temperature to increase, decrease, or remain the same? 300, you can see it is decreasing. Similarly, temperature 250 degrees Kelvin, can expect the temperature increase, decrease, or remain same. Here also is increasing, but a reduced rate of increase. 250 is decreasing, I'm sorry, decreasing, but reduced rate. Now we'll go to the next model. Here we are changing the epsilon value to be 0.5. And we just saw what will happen. So that means we are reducing the outgoing radiations due to greenhouse, 0.6 to 0.5. Now if you look at the graph now, we'll find there is another, you see the more orange color, that is epsilon 0.5, the blue color is epsilon 0.66. Now you see in the same range we have taken 200 Kelvin to 400 Kelvin. Where the 0 now? So 0 is coming around 300 Kelvin. So there is a new equilibrium for the ordinary differential equation you are considering. What does that mean? What does epsilon contribute to global equilibrium temperature? Let's see the planetary equilibrium temperatures. So if greenhouse gases is increased, epsilon will go down. In that case, the planetary equilibrium temperature also goes increased further, become hotter. Thus, after a small perturbation, the average temperature tends to be restored to equilibrium. Equilibrium means what? Even if you shift the values, it again comes back to that. It must be adjusted. That's equilibrium temperature. This plot Ft reported as phase line because it contains all information about the dynamics of the systems. Now we'll go to next model. Here, by reducing the outgoing radiative energy by the factor of epsilon, we are able to match with the current climate state. But aerosol, dust, greenhouse affects only the outgoing energy. They are not only outgoing, they also affect the incoming energies. By blocking the incoming solar radiation, they present it. It's in the Earth's surface. Okay, albedo. So, what do you think? Release of the aerosols and dust affects the albedo? Yes, if you release more, then albedo definitely increase because they will also create reflective surfaces. So, can you found relation between albedo and atmospheric particulate matters like aerosols, dust, and all this? So, you'll have some temperature dependent albedo because albedo you can't measure directly. So, you are going to use albedo as a function of temperature. How? Let's assume that the albedo depends on the global average temperature in such a way that it decreases monotonically from high value 0.7 to low value at low and 0.3 at high temperatures. So at low temperature 0.7, high temperature 0.3. Why do you come to this statement? Because if you take ice, it's cooler, in that case reflection is more. In water, a little warmer, reflection less. So you can find as you chill, the reflectivity is increasing, albedo is increasing, and it getting warmed, albedo decreasing. So that's why the time dependent albedo concept we are taking. So in that case, alpha replaced by alpha into alpha is a function of time, alpha t. So what happened? The whole equations here you find alpha t is a function of we mentioned that the reflectivity function of temperature. So you find one equations and which assume that the alpha t is a function of time, temperature in the particular relationship 0.7 minus 0.4 into exponent e to the power t minus 265 by 5 divided by 1 plus e to the power t minus 265 by 5. So that is, you take a particular equation. This is empirically evaluated equations. We will see this will explain this equations plot. You can see this plot. The two values are there, 7 and 4, and with the decrease. These functions. So incorporate the temperature dependency albedo, this function. Then C dt d capital T by d small t is equal to q into 1 minus alpha alpha a function of t and subtract by epsilon sigma t to the power fourth. So here just replace alpha by a function of t, alpha is a function of t. Now these two components will take a plot. One component, the first part, incoming and outgoing. L is q into 1 minus alpha function of time, sorry, temperature, this first function, and second one is epsilon sigma t to the power fourth. So when we take these two components separately, we find some interesting patterns. See, both the cores intersecting each other 3 points. So these are the points where both are equal, 3 points. So first T1 to 88 degree Kelvin with the present climate, and then that is other 2 points T2 265 Kelvin and T3 233 Kelvin. So 3 points you get. Now observe these 3 temperatures, you find small perturbation T1 and T3 would not make much difference because they are more stabilized. But in case of T2, if it increase little bit, it will go to the T1. If decrease, it will go to the T2. It is an unstable equilibrium. So what is the meaning? We are observing that the equilibrium T3 corresponds to climatic state where more than 50 degree cooler than the current climate, because T1 is understandable, present climate. So 50 degree cooler than the current climate. So this is also a stable equilibrium. So that means it's possible that we can have, our climate can have an equilibrium state at such a low temperature, 50 degree cooler to 33 degrees centigrade, we can have a equilibrium state. Yes, climate can have multiple equilibrium states. At least this model establishes that there could be 2 stable and 1 unstable equilibrium state. So far we have assumed that Earth radiates like a black body. So the outgoing E out follows the Stefan-Boltzmann's law. But satellites have been collecting data about the energy radiations from the space of the Earth since 1970s and indicate that it's sort of grey body, not exactly black body. What does it mean? It means it's not it is not 100% ideal black body. The outgoing energy follows some sorts of linear relationship. So this some A plus BT, some type of relationship. This satellite data strongly indicate the variation of outgoing radiation, so the temperature is better presented by these simple linear functions. FBS, function of temperature, function of time, is equal to A plus BT. The subscript BS refers to the meteorologist Michael E. Budioko and William S. Sellers. So Budioko and Seller, they are the 2 scientists who have proposed these corrections in the black body concept into grey body. So propose this formula in 1960s, well before the satellite data became available. At the time itself they proposed 60s. If the temperature is measured in degree centigrade, remember previous consideration is Kelvin. Right now this studies are done based, the empirical study based on degree centigrade. The best fit of the observational data and the northern hemisphere was fitted with A is 203.3 watt per meter square and B is 2.09 watt per meter square and degree inverse. So this is the value, empirical value they obtained in the northern hemisphere. So the incoming radiations remain as before, pi r square s 1 minus alpha function of time, whereas the term outgoing radiations sigma t to the 4th, which was Stefan-Boltzmann's conceptions, we replace that by A plus BT. Now when you equate both the incoming and outgoing at equilibrium conditions, pi r square cancels both sides and replace q by s by 4. So you get q into 1 minus alpha function of t is equal to A plus BT. Similar to previous model, we plot the incoming radiations, the first part q 1 minus alpha to the function of time, sorry, function of temperature, and the outgoing radiations also A plus pt, because you already know the values. So plot both of them. This become a plus pt will become a straight line, and the previous one will be, previously it was the fourth order polynomial because t to the fourth was used. Also find similar patterns again. 3 equilibrium points, 2 stable, 1 unstable. Although the points were little different. Out of these 2 stable states, one corresponds to the present temperature and others are 50 degree lower. So what is the conclusion? Modern satellite data are consistent with the earlier observations that the climate systems can have another much colder equilibrium state besides the current stable state. The snowball earth conditions of the earth may probably refer to the glacial age, refer to the geological time scale with 750 to 580 million years back. That time it was supposed to be like this. So I shifted the equilibrium from the present. What shifted the equilibrium from that state to present state? Most likely it is the greenhouse gas, and because of that associated with the biological activities. That's it, could have been shifted. So this we cover the basic energy balance model for climatic changes. Now when you add the circulation patterns, the model become more complicated. That is beyond the scope of the present studies. But in that case, predictability would address to all these variation parameters. Thank you.